fishnet limit.
Okay, thank you very much for the introduction. So, like the other speakers, let me thank the organizers for setting up the conference and for inviting me to speak. And also thanks to the organizers of last week's workshop. And a particular thanks to Enrico, who sent me so many emails both before and during the conference. I'm very impressed. So, I will be talking about integrable monopoles and what I will call a fishnet limit. So by monopoles, I mean magnetic monopoles, and by a fishnet limit, I mean something which will hopefully become clear during the talk. And what I will be reporting on is based on some paper that I wrote together with Kristjansen last year, and some ongoing work. Oops. Do I have to point somewhere else here? Sorry. Okay, no, I think it's me who is not working well. Okay, so why should we care about these monopoles? Here I cannot resist mentioning again this citation from Joe Polchinski, who said that the existence of magnetic monopoles seems to be one of the safest bets that one can make about physics not yet seen. And that's a statement he made 20 years ago at the Dirac Centennial Symposium. So what I will be considering is actually a four-dimensional quantum field theory which contains both a monopole and a Higgs particle. But my main motivation will not come from experiments. Of course, I will consider our favorite n=4 super Young-Mills theory. So my motivation from the point of view of this conference is that by inserting a monopole in this theory, I can construct a novel example of an integrable defect CFT. So the defect is simply the world line of the magnetic monopole. So it's one-dimensional, and it creates for me a defect CFT which is of codimension 3. And if I choose the parameters in a good way, then I can also ensure that it's a half BPS. There's also a good motivation to study this from the point of view of the last week's workshop, because this setup should also be amenable to the boundary conformal Bootstrap program. It has not been considered at all. And n=4 super Young-Mills theory also has the duality known as S-duality, which is an electric-magnetic duality under which a 't Hooft line is dual to a Wilson line. So if our 't Hooft line is integrable, maybe we will learn something new about Wilson lines and S-duality. And finally, we have introduced some novel fishnet limit, which makes it possible, or in which we can at least obtain some exact results at strong coupling for a Wilson line in the background of the 't Hooft line. Okay, so the plan of the talk is that I will first introduce this monopole Higgs setup, and then I will explain how to quantize n=4 super Young-Mills in this background. This quantization, it will involve some very nice and exactly solvable quantum mechanical problems, and their solution will really reveal to us the underlying integrability of the theory. Then after the quantization, I can in principle compute anything I like. And one thing that I would normally calculate are one-point functions, which are supposed to be exactly calculable, because this setup, as I said, is supposed to be integrable. But I will not consider that. Instead, I will consider a Wilson line in the monopole background, and in particular limit of the perturbative computations. And I will finish by some conclusion and open problems. Okay. So a magnetic monopole, it's a point-like object, which I'm not sure what this one. Where's the pointer? I cannot really find the pointer. Sorry. No. Here. Sorry. Okay, it's a point-like object which gives rise to a radial magnetic field, as you can see up there. And we all know that if magnetic monopoles exist, then their charge will be quantized, as was pointed out by Dirac already in 1931. And I should say that I use convention where I set all the constants of nature equal to 1, including the electric charge. So my Dirac quantization condition is simply that this parameter b should be an integer. And as I say, I will consider a monopole which is static at the origin, and then its whirl line will simply be a line in the time direction. And from the view of quantum field theory, the way one describes such an object is as a disorder operator. It prescribes a certain singular configuration of the gauge field, and then you have to perform your path integral with those conditions as your boundary conditions. Sorry, can you? Okay, but where do I find the pointer itself?
This is up and down, and you want the pointer, the red dot?
The red dot, yes. Okay, I'm glad you also a little bit confused.
I think you have to... Ciao. Pedro, do you know? Because...
A pointer, yes.
But the pointer, definitely you don't want to point there, right? But the pointer should be the top one. But the pointer is just the top one.
This one?
Yeah.
Okay. Okay, good. Thank you. Okay, so the singular configuration for the gauge field takes the form written here when it's expressed in spherical coordinates, and you see that it's singular at theta equals pi, but not at theta equals 0. Well, you can also define it so it's singular on a half line, but you can also define a similar configuration which is singular in the opposite half line, and then the two should be connected by a gauge transformation, and the requirement that this is the case gives you the direct quantization condition. Okay, so this is something which was understood a long time ago. Now we want to insert this monopole in n equals 4 super Young-Mills theory. So now, of course, our gauge field and our B field, they are in cross n matrices because we have non-abelian gauge theory. So B becomes a matrix. And on top of introducing this classical value for the A field, if I introduce also a classical expectation value for one of the scalars or some direction in the SO6 space, then I can obtain a configuration which is supersymmetric. So I can take this B field to be any element of the Tang algebra of UN, but I take it just to be a diagonal matrix with a 1 in the upper left-hand corner. That's the simplest configuration I can consider. And the VEF of the scalars I take to be given just by this simplest possible 6 vector, which means that only one of the scalar fields gets a vacuum expectation value. That configuration, it conserves half of the supersymmetries. And due to this scaling of the classical fields, I obtain a one-dimensional defect CFT of codimension 3. And that's the guy I want to look at. Okay. So this setup, it involves various types of dualities, which we can use to learn about the system. So first of all, there's a usual ADS-CFT duality, and that tells me that this setup is dual to a D1, D3 brane system. So the D3 branes are the usual ND3 branes, which generate my Minkowski space. And then I have in that background a single D1 brane, which intersects the stack of D3 branes in a line, which is exactly my 't Hooft line. And Dickel and Oos have listed the possible boundary conditions for open strings in various brane setups, and this setup is one of those which are supposed to be integrable. So therefore we also expect the gauge theory setup to be integrable in the sense that we expect to be able to compute one-point functions exactly. There's another duality of this setup, namely S-duality, as I mentioned, and This is a duality which involves a change of the coupling constant in this form here, which interferes not only with weak-strong coupling, but also with a large n limit. And as I said, under this duality, a Wilson loop is dual to a 't Hooft loop, whereas something which does not have any electromagnetic characteristics, such as a chiral primary, does not transform. And one has certain results for correlation functions of chiral primaries in the background of a Wilson loop, which give us predictions for the same quantities in the background of the 't Hooft loop, and one can check that that this prediction is confirmed. But on top of that, this is something which has to do with protected operators. Integrability also give us access to non-protected correlators. Okay. Yes, so let me quantize N=4 super Yang-Mills theory around this background. So our starting point is that we have to expand around the classical fields, and under that expansion, the various field components of our quantum fields behave differently. It's only the field components in the first row and the first column which are really influenced by the monopole. This big matrix down here is uninfluenced. These components behave as in free N=4 or in usual N=4 super Yang-Mills theory, and this one as well. Then to set up the perturbative program, you have to invert the quadratic part of the action of the theory after gauge fixing, of course. And this is where the quantum mechanical problems come into the game, because what you need to do is to invert the quadratic part of the action, which I've written here in a schematic form, where g-1 is the inverse propagator. So to find the propagator itself, you can solve for its eigenfunctions, and then you can find the propagator by doing a spectral resummation like that, where you take 1 over the eigenvalues, and then you do an outer product of the eigenfunction. It's a textbook method which we apply here to do the quantization. And it's only the field components here of type beta which really are influenced by the monopole and which really needs to be treated by this method here. Okay, so there are 3 types of fields which behave or must be treated differently in this quantum mechanical framework. There are some fields which are what we call easy fields. These are the scalars without the webs and the time component of the gauge field, and then there's also a ghost. And these, when we solve the quantum mechanical problem, they behave exactly as a scalar which is living in a monopole potential. Then there's the last scalar field and the gauge field. It turns out that they couple to each other, so we have to solve a quantum mechanical problem which involves the scalar and a vector particle in a monopole potential. So the first problem was actually solved already by Dirac, and several other people in the early days of quantum mechanics also improved on his solution. The case of a spin 1 particle in a monopole potential was solved in the 90s by Olsen and others, but our problem is a little bit different, and you will see that the underlying integrability of our model actually makes this problem nicer than the single spin 1 problem. Finally, for the fermions, we have the problem of a fermion in a monopole potential, which, however, is not the standard monopole potential, because we have an additional term coming from the interaction between scalars and fermions in N=4 super Yang-Mills. The standard case was solved in the 70s by Kasama et al., but our case is not quite standard. But all these problems can be exactly solved, and their solutions are actually more beautiful than the standard solutions, I would say. Okay, so here is first the scalar case, a scalar in a monopole potential. Then in that case, the inverse propagator, the quadratic term of the action, looks like this, up here with a time derivative and then some Hamiltonian, which is the standard Hamiltonian of a scalar in a monopole potential. And we solve it by, you see it has a flavor of a particle in a central potential, so we solve it by the standard method of separation of variables. So we factor out the time dependence, and then we're left with some angular momentum problem. And for that problem, one can introduce standard or angular momentum operators with standard SU2 commutation relations, which commute with the Hamiltonian. And then we also know from SU2 representation theory how to write down the eigenfunctions. So the eigenfunctions, they will be given in terms of what is known as monopole spherical harmonics. They are not the usual spherical harmonics, but they are expressed in terms of Jacobi polynomials instead of Laguerre polynomials. So they have also the usual exponential prefactor term here, but that is shifted by b/2, where b is my b from before. And it's simply due to the fact that the field carries also some angular momentum. And the quantum numbers J and M, they are the usual ones of the central potential, so they are integers or half integers. And so we learn from this that if we want a wave function to be single valued as we want for a scalar, then this quantity b has to be integer. And that's another way of seeing the direct quantization condition. And you also see the interesting phenomenon of a spectral flow, that if we start out with b being 0, then the angular momentum has to be integer, but if we turn b to 1, then it suddenly has to be half integer. And we go on to b=2, then it has to be integer again, and so on. So the spectral flows as a function of the parameter b. Okay. But we have a completely explicit expression for the wave function in terms of these monopole spherical harmonics, and the radial part becomes some Bessel function. Okay, and that means that we can use this process of spectral resummation. We have to sum of 1 divided by the eigenvalues, which is one part from the time dependence and one part from the angular dependence. And then we have to take this out, the product between the wave functions. So there's some part from the spherical harmonics, some part from the Bessel function, some part from the time dependence. And this is of course completely explicit, and we can even simplify it a bit. We can integrate over omega by contour integration, and we can perform the sum over m. And if we do that, we end up with this equally explicit expression where the angular dependence is encoded in some Jacobi polynomial, eta is n dot n, within some unit vectors on the sphere, and then the dependence on the radius and the time is encoded in some object here, which is simply an ADS2 propagator. So the full propagator is a product of a spherical propagator and an ADS2 propagator, which is of course to be expected given the symmetries of the problem. We have an ADS2 space, an auxiliary ADS2 space, which has the TOF line as its boundary and the distance as its radius. But it also comes out very explicitly, like here. Okay. Then let me move on to the vector. As I say, it couples to the scalar field, which gets a non-vanishing vacuum expectation value. So you have some 4x4 mixing matrix here that you now have to diagonalize to find the propagator for these two fields. And we have already solved the problem of a scalar in the monopole potential, so, and now we add a vector, and we know how to add angular momenta in quantum mechanics. So we know a good quantum number will be the sum of the angular momentum from before and this spin 1. And this we can use to make a mode expansion, and as answers for a mode expansion of the scalar and the gauge field. So we expand the scalar in the monopole spherical harmonics from before, and for the vector field we use vector monopole spherical harmonics, of which there are 3 different ones for a given value of j, corresponding to the 3 ways you can compose the angular momentum. And then we can assume that the radial part is given by some Bessel function again. And now you see in this ansatz I have for each value of the total angular momentum, I have 4 unknowns, these coefficients, the c's, and this nu here, which is the index of the Bessel function. And it turns out, if you write down everything carefully, that these quantities are given as the eigenvalues and the eigenvectors of some 4-dimensional 4x4 numerical matrix. So they can be found explicitly. And although that matrix looks a little bit complicated, the solutions which come out are very nice. The possible values for the indices of the bezels, take these values here. One is degenerate, and then the two others are different. And it also turns out that these eigenvectors are not too bad, although the matrix looks very ugly. And this is actually interesting to contrast to the case where you only have the gauge field and not the scalar, because in that case, these indices of the Bessel functions are much more ugly. They are not even rational numbers. They are actually irrational. So this needs simplification. It actually comes exactly because we have coupled this scalar to the gauge field, which is something which is dictated to us from the action of n=4 Subayer-Mills theory, and which again is dictated by the requirement of supersymmetry. And then we, of course, again can find our propagators by this spectral resummation that I explained before. Finally, there are the fermions, which, as I say, they live not only in the standard monopole potential, because there's also a term coming from the interaction of the scalar fields with the gauge fields, with the fermions. So we need to solve some fermionic eigenvalue problem, where on top of the usual monopole terms, we have some additional off-diagonal terms which appear here and depend on the monopole charge. So here again, you do an appropriate mode expansion, which is now in terms of spinor spherical harmonics, and you have now to put a little bit more general ansatz for the radial dependence, whereas the angular dependence is taken care of by these spinor spherical harmonics. I don't want to go into the details, but just show this neat simplification, which again appears because of the coupling to the scalar field. So in the standard monopole potential, you have some wave functions which involve those spinor spherical harmonics, and then some Bessel functions which are indexed by a quantity mu, which takes this form here for general J, and which again is in general an irrational number, not very neat. But when you couple to the scalar field, it turns out that the relevant Bessel functions, again, they become not half-integer valued, but integer valued. And again, this simplification is something which is dictated by the supersymmetry of n=4 Subayer-Mills, and which is a reflection, I believe, of the underlying integrability of the model. Okay. So now we've set up the perturbative program, and we can move on to compute anything we like in perturbation theory. So typically I would now start to talk about one-point function and how to study the integrability properties. But today I will tell you about another computation, namely the computation of the expectation value of a Wilson loop in the background of the 't Hooft loop. So we consider, of course, a Maldacena Wilson loop, where on top of the gauge field we also have a coupling to the scalars, given by some constant vector nu I with 6 components. And now I reintroduce this general vacuum expectation value for the fields, which was given by a constant 6 vector ni, and appeared in the expression for the waves in this way here. So now we have these two vectors on the phi sphere, and not surprisingly, the angle between the two, cosine phi, will be an important parameter for the problem. Okay. And now we want to compute the vacuum the expectation value of the Wilson loop in the background of the 't Hooft loop. And we expect that it will have this exponential behavior here. With the conformal theory that we have, we don't really have other possibilities. And our aim will be to determine this alpha here, not only perturbatively, but actually at strong coupling in a particular limit. So we start out perturbatively. At tree level, we simply insert this value for the classical field, and you can immediately see that this expectation value will be this exponential plus n-1. So the n-1 come from all the diagonal elements here, which are 0. And this one comes from the diagonal element in the upper left-hand corner. And you see this is it's maximal when phi is equal to 0. Then it goes to 0 when phi is pi over 2. And then beyond phi equals pi over 2, this term here dominates, and there's nothing interesting to see. But we want to move on to higher loop orders, and it's not that I want to drag you through the one loop computation or higher loop computations, but we need to look at it to have the idea. So we start by computing the one loop correction, and there are contributions from two different diagrams, one coming from the scalar and one coming from the gauge field. And we are of course only see something from those fields which are affected by the monopole. So here we get a contribution from scalars like that, and a contribution from the temporal component of the gauge field, because the Wilson line lies in the temporal direction. Yeah, only 1 minute. Okay, I'm sorry. How should I finish? Okay, we have computed these propagators, so we can of course insert here and compute the one loop correction to this exponential behavior of the Wilson line. And it turns out that this difference here becomes a telescoping sum and finite, and we can write it down explicitly. But what is more important, we can now take a particular limit which allows us to resum the perturbation series to all orders. And we call it a fishnet limit because it's somewhat reminiscent of what other people call the fishnet limit, in the for the reason that we take a certain limit and multiply by a certain angle, multiply by I, and send it to infinity. Normally in the fishnet limit you would then send lambda times this e to the I phi to infinity, but here we keep lambda fixed. However, we still take n to infinity. And then you can argue which diagrams are important in this limit, and it turns out that due to some particular large n counting, diagrams of this type are not important, and because of this limit, diagrams which have vertices are also not important, so only these type of diagrams are important. And one can write down a recursion relation to determine these diagrams. This recursion relation can be massaged into some integral differential equation that we can solve by Laplace transform. And the solution for the Laplace transform of the Wilson loop takes this form here. And of course we can easily find out what the exponential behavior is by looking at this pole, the pole of the Laplace transform. And if we do that, then we find out that this the relevant pole is given by some quadratic equation, and we can actually find it in that fishnet limit. And if we do that, we end up with this expression here for our exponent in the exponential behavior of the Wilson loop, which has many nice features. So first of all, you see it has the correct strong coupling behavior. It behaves as square root lambda when lambda goes to infinity. You can take the strong coupling limit and you get this expression here for alpha, which actually is completely compatible with string theory. We can reproduce this by a string theory computation, which involves a minimal area computation. And it also reproduces a well-known radius of convergence for n equals 4 super Yang-Mills that we have seen before in various different computations. Okay, let me finish here and put the conclusions. Magnetic monopoles are fascinating. We have completed and streamlined their quantization, and thereby provide a novel example of an integrable defect CFT of codimension 3, and provided novel exact results for Wilson loops in a fishnet limit. And let me leave this slide.
Okay, thank you. Any questions? Joe?
What's the string theory configuration that you actually compute this, compare it to?
It's on the previous slide. It's like this. You have the 't Hooft loop pointing inwards here, and the Wilson loop likewise pointing inwards at a distance r. Then you have to find the minimal surface which extends from the Wilson loop into the D1 brane in the interior.
So the D1 is going
It's
radially-
vertical, yes,
Okay.
and intersects the boundary in a line, which is a 't Hooft line.
Okay, so the other part coming up, okay.
It's just as
Actually,
it's a trick of solution, because the solution is known for this more general this quark anti-quark potential where you have two Wilson lines. They're the minimal per. Yeah. Okay. Mm.
No?
There are some considerations about the 't Hooft loop in the Wilson loop background, but I don't remember how far they go. We can look it up. Yeah. Mm.
So if you consider quantization of particle in a Coulomb potential, there is like this Runge-Lenz symmetry.
Mm.
Is there something similar for the monopole?
Oh, that's a good question. To be honest, I don't know on the top of my head, but since it's integrable, I would expect some charges of that type. Yeah. Mm-hmm.
Do you see any, sorry, do you see anything similar to the Witten effect? Like if you do T duality, you shift the theta angle by 2 pi, then the electric charge should take a contribution from the magnetic charge of the 't Hooft monopole. Can you see this explicitly somehow?
T duality.
So there is this classical result that if you have a monopole configuration, and you put an electric charge there, and you go around the monopole, so you take a monodromy around the monopole, then the electric charge gets enhanced by the magnetic charge. Okay, no, maybe it's too strongly coupled. Never mind. And then I have another question.
Okay.
And the other question is, I'm a bit confused. So the 't Hooft line should depend also on some representation theory data, right?
That's true, yes. I jumped that a bit. I mean, this Wilson line is in the fundamental representation,
Right.
because I have this simple B field, which is just a 1 on the upper left-hand corner. In general, you can take any set of diagonal elements, and they can be translated into a representation label for the dual 't Hooft line, Wilson line.
Right, but then I should expect some kind of non-mutual locality when you like if you fix the gauge group to be SUN or UN, doesn't matter. There are some Wilson line 't Hooft lines that are non-mutually local to each other. Can you still take correlation function of 't Hooft lines and Wilson lines that have the representation theory charge commuting to each other, or?
I cannot hear the question, but we have only looked at this as simple representation. But in principle, one can do exactly the same game for a general representation.
Okay.
And difference between the diagonal numbers appear everywhere, of course.
Okay,
Yeah.
thank you.
If you imagine deforming slightly the straight line, what type of operator would that result in with an insertion?
You mean the deforming the 't Hooft line, or?
No, like
Or-
the counter deformation operator in Wilson line.
Yes.
What would it be the analog here? Because it's like you,
For the 't Hooft line, you mean, or what?
yeah.
It's an interesting question. I don't know if the answer is known. Are you asking what the displacement operator looks like? Yeah, that's an interesting question, but you have to take some careful limit, because you have this divergence as 1 over r. But of course, correlation function of the displacement operator can be computed and so on.
Okay, I think that just to keep on schedule, we'll leave further questions for the coffee. Thanks, Charlotte, again.
Okay.